Hello and welcome to this low-level JavaScript series on building Parser Combinators from scratch. This is the fourth episode in the series, and if you want to check out the rest of the episodes, there's a playlist linked in the description below and on screen above. Now, in this episode, I mainly want to write a method called chain for our parser, which is going to allow us to write something called a contextual parser. And what that really means is that we can choose how we parse the next piece of data based on what we've just parsed. In many ways, it's a more generalized version of the map method. So let's first have just a little recap on how the map method works. In the previous episode, we wrapped up the system into a class, and we wrote some generic and useful parsers, like the many, combinator, and letters and digits. But by far the most impactful thing we did for the entire library is actually that we wrote a method called map. Now, map, if you remember, is very similar to array.map. And basically what we can do is we can give it a function and it returns to us a new parser whose value has been transformed by the function we gave it. This is extremely useful for creating structure or for creating utility parsers based on existing parsers. For example, let's take a little look at how we could create a utility parser called between. And that's going to take two parsers, a left and a right, and then finally a content parser. And it's going to try and parse first the left parser, then the content, and then the right parser. So it gets the content which is between two other parsers. And that's really useful for things like matching stuff between brackets or matching things between quote marks or anything which is a sequential thing of three parsers in a row. So how could we write such a utility parser? Well, first of all, let's scroll down. Let's create a function called between. And between, like I said before, is going to take a left parser, a right parser, not a right, and a content parser. You might think, oh, okay, we're gonna return the new parser. That's going to take our parser stage transformation function. But actually, we're not going to do that because all we're going to do here is we're going to run sequence of, and we're going to open an array. We're going to put our three parsers in here: the left parser, the content parser, and then finally the right parser. And what we're going to do after that is we're going to map the result. So now we have an array of results, and we know that in the second position in the array here is the content. So all we have to do is to bring that out, and now we have a really generic and a very useful parser that we can use to match things which are between. And we can actually make this even more useful by sort of separating this out into a curried function. So we first provide the left and the right parser, and that gives us a new function that when we provide a content parser, that's going to let us get the actual content we want to get. If we have something like this now, a string like this, we should be able to isolate that. Let's try it. So you see here our target string was hello between brackets, but what we actually got was hello, just the string. And actually the index is at 7, so if you were to count that out, you'd realize we were actually here, so we're going to keep parsing afterwards. And that must make sense because we use sequence of. So we're beginning to get to the point with our parser library with things like map, where we don't have to write every single parser from scratch. We can actually start to just combine what we have and use map to sort of selectively extract structure or imply a structure. Okay, so next what I want to do is I want to pose a question. Let's imagine we had some input data that looks a little bit like the following kinds of examples. So I'm just going to write some examples out here. Let's make some space. Let's imagine we have an input that's like this, string, colon, hello. That's going to be one example of something that we want the parser that we write to be able to extract. But we also want to be able to use the same parser to get things like this. And you can already see here where this is going to start getting tricky. Or maybe it's not super clear yet, but hopefully it will become clear. And third, just to add something that's a little bit more interesting in, I'm going to add in a dice roll. And we're going to use like the sort of old school Dungeons and Dragons representation for this. So something like 2d8, which means roll 2 8-sided dice. So we want to write a parser that is able to extract those kinds of strings. And just to imply a little bit of constraint on this problem, because it's it would be quite easy to write a parser that would be able to match all three of these things, but we want to do it with structure. So when we run the parser for these three strings, what I want to get out is an object, something like this. So for the first, I want to get something like an object that has a type. The type will be string. And it's also going to have a value property, and that's also going to be a string, and it's going to be the string hello. Okay, and for number, we're going to have a type number, but here in the value part, we're actually going to have the number 42. So I don't want this to be a string, I want it to be the number 42. And finally, we're going to have our dice roll result. And that's going to have a type dice roll. And it's going to have a value, and there's many ways you could represent this, but I'm going to represent it with an array, and I'm going to say that it has 2 and 8. So that's going to, the first item in the array will represent the number of dice, and the second will represent the amount of sides that dice has. These are the three kinds of results we want our one single parser to be able to extract. You might already be thinking, how could we do this? Is it possible? Spoiler alert, it's not possible with our current system. In order to do something like this, we're going to have to write a chain method. And I will explain more about that in a moment, but first what I want to do is I just want to write the individual parsers that will be able to extract, let's say, this part of the information and then turn it into this, just so we can see that that is possible, because that is possible at the moment. So let's have something called a string parser. It's quite simple, it's going to be letters. And we'll map the result of letters to be an object that will have a type string, and it will have a value of the result. Now, number is going to be quite similar. So we'll have a number parser, but this time we'll use digits. We're going to have a result. Type will be number. And the result is going to be a string, because we just extracted this from a string. So let's convert this to a number. So we can wrap that up in number. And the dice roll is a little bit more complicated, but not so much. Dice roll parser. That's going to be, let's say, a sequence of. And so we want to be able to get first a number, then the letter D, and then another number. So we'll get digits, we will get the string D, and finally we'll get digits again. And then afterwards we can map all of that to an object with a type, dice roll, and a value of an array. And what we'll do here is I might even destruct this. So we'll first have our n number of dice. We have the letter D. I'm just going to put that in an underscore because we ignore it. And S for sides. And here we'll do the same trick. We'll do number. Okay, so these three parsers should be able to extract these three kinds of strings that come after the colon. But how can we wrap that up into a single parser that when we run it on any of those three strings, we'll make sure that we get these three outputs? So what I want to do before we actually go and implement chain is I want to show you how we'll actually use the method to solve this problem before we've actually written the implementation, because that will be clearer why we're going to do what we're going to do. This should be S. I apologize to those who were screaming at the screen. So let's get rid of this, this old parser here. Let's write our new parser. So what we want to do, if we look back at the strings that we have here, we first have a string followed by a colon and then the kind of specific parser that we want to have. So what we first need to do is parse this string, which is just letters. And this is going to be a sequence. You can see this is already going to be a sequence. So let's write it with a sequence of. And I'm actually going to embed a second sequence of in here, because we need to get the string, but then we need to also match this colon. And I want to throw the colon away. So what we can do is to say, first get letters, and then we'll get the string, which is a colon. And then we're going to map here, and we're just going to throw away the second result. So we'll take our results, and we'll just extract the first result. And we can probably nicely get that all on one line without that being too ugly. So this is going to give us the value here. And actually, we don't need the outer sequence of, so we just need this one. And from here, after we've mapped, I want to run chain. And chain is going to give us this single string. So this is going to be the type. So let's actually just call it type here in the function. And what we'll do is we will, based on that type, if the type is string, we're going to return letters, because that's how we parse our string. Oh, that's not true. We're going to return the string parser, because that's going to transform the structure. But if the type is number, then we're going to return the number parser. And this is not a great way of doing it, because this can lead to some errors, of course, but I'm just going to immediately return the dice roll parser if we're not able to do anything else. So this parser, what we're saying here is first parse the initial part of the string. So first parse the dice roll along with the colon, then throw the colon away, and then run this through chain, and based on chain, return the next parser and use that to continue parsing. So it's a bit of a lot to take in, but basically this whole operation just produces a new parser that will be used to continue to parse results. So it's going to consume all of that input along the way and finally give us back our structure in the end. So with this in mind, let's go up and see how we can implement chain. Chain is very, very closely related to the map method. In fact, as I said in the beginning, chain is a more generalized version of map. We can actually write map using chain, and I'll maybe show that at the end. But chain is just like map, and it's so much like map. I'm going to copy map, and we're going to base our implementation on that. So these first two lines aren't going to change. This first line that we run here inside the new parser is simply getting the next state of the parser, and that should make sense because chain is a method, just like map is a method. So that means that we have something like this. And we have to first run this parser before we can get the result from it. So that's what's happening here. We're actually running the parser on the parser state, and this is just whatever is coming in before. And what we get back here is the resulting state. We need to get our next state. We need to, if there's an error inside the state, we're just going to return it. We don't want to continue running the chain method because we only want to run chain on valid parser states. We don't need to actually update the result and transform the value using the function. We need to use the function to get the next parser. So I'm going to write a next parser variable here. And what we're going to do is we're going to run our function on next state dot result. This is going to give us a parser. And what we can do at the end is to simply run this parser on the next state. So what we do here is we simply return, now it's not this dot parser state transformation function, it's next parser dot parser state transformation function. And to this we pass the next state. So let's actually test this out. Luckily for us, we've already written the implementation. So all I have to do is to take some of these strings. Let's cut those, bring them closer down here. And we can get rid of these examples now. And let's try these strings. So first, we try string hello. And if we look here in the results, we'll see our type string, value hello. Let's try the next one, number 42. Finally, let's see if the dice roll works. Yes, so we have everything that we need. And so without going into too much detail, this system and the inclusion of chain has allowed us to build up a system of parsers that is much, much more powerful than many other traditional methods of parsing. This ability to look back at what you just parsed and base your next move on that result is something that a lot of systems don't have. I don't want to give the illusion that Parser Combinators are perfect or they're the best kind of parsing system. They have their own drawbacks, and we may get into that towards the end of the series. But this is quite a useful tool, and if you start to write interesting DSLs, you'll find many places to use this kind of thing. And let's just take a little look at the implementation again. Now, that's only 4 lines of code there, but I don't want to give the illusion that it's simple. When I was first wrapping my head around this idea, it took quite a while for it to sink in. But when it does, I think you gain a really solid understanding of exactly why this system is so powerful. The 4 lines we implemented here allows the parser system to recognize a whole range of grammars that aren't even possible with other methods of parsing. So you might also be wondering why this method is called chain. It doesn't seem to relate to the idea of parsers in general, and that's true. It's actually a much more general concept from functional programming, just like map. For something to be like mappable, in air quotes, there needs to be a sort of sensible way to create this map method. And the sensible way is, well, for arrays, it simply means transforming all the values inside the array using the function that you provided. And with parsers, it means transforming the value that comes out of the parser using the function. So they're clearly very, very similar ideas. They both sort of treat the object as if it's a container. The array is actually a container, and the parser is not really, it doesn't really contain a value, but it's sort of like it will eventually have a value. Now, arrays actually also have a chain method, but it's not called chain. It's called flatmap. And in many other systems, chain is often known as flatmap, or it might be known as bind. In flatmap, the array takes a function, and that function runs on every element of the array, but then the function will always return another array. And then in the end, the array is flattened out one level by all the arrays that were returned. And maybe you can see the similarity to a parsing system here, because what we do is we run our function, and instead of returning a value, we return a parser that will return a value at some point. So, and then we flatten it out because we don't keep the parser inside the result, we just keep the new parser. So we've sort of flattened the parser out in a way. We went from one parser to another parser. So in functional programming, we call things that can define a map method and a chain method. I say method, there's other ways of defining this, but if you can define map and chain for a special kind of object, we call that a monad. Now, that's not strictly true, and the word carries a lot of baggage, and I'm not going to dive into the really, really nitty-gritty details of what makes a monad. But it might just be nice to understand that on a very practical level, like that's the only thing it is. It's a special kind of object that basically implements an interface. And the only real impactful thing there is that the interface must adhere to certain kinds of principles, and it needs to be something sensible. It needs to make sense with the idea of what mapping and chaining is. So the reason I mention it is because the underlying functional programming concepts here are a really interesting area of software engineering, and many even senior developers and programmers will either sort of completely ignore functional programming ideas, or they'll wait decades before they try to understand it. I'm not the world's most passionate functional programming advocate, but I certainly think that it's worth knowing. Even if you're not building a 100% pure functional programming system, you can see the ideas which are useful to take and use in projects, and that will make you a better developer. If all of that went over your head, it really doesn't matter. We're not going to dwell on it, and we don't need it for the rest of the series. If you do want to learn more about this, I'm going to leave some links in the description to something called the Fantasyland specification, which is the JavaScript specification document for algebraic structures. And it describes how you need to implement these interfaces in order to be compliant with a whole bunch of extra libraries and helpful things. And it's a whole ecosystem out there. In the next episode, we're going to try and understand how we can use our Parser Combinator system to parse recursive data structures. By recursive data structures, I mean, imagine parsing something like a string that represents an array, but inside that array, there could be more arrays, but there could be regular items and there could be more arrays. So when we define what is an item, it can be either, let's say, a number, or it could be another array. So we need to figure out how we could write a parser that's able to handle those kind of situations. It's a really key concept in parsing, and if you're going to ever parse any kind of programming language, DSL, configuration format, you're going to need to do some recursive parsing. And just because of some of the quirks of how JavaScript works as a language, we're going to have to approach that in quite a specific way, maybe a different way to how you would do it in other languages, but still, I think it's going to be interesting. So I hope you've enjoyed this installment of the series. If you have any feedback, I'd love to hear about it in the comments or in the low-level JavaScript subreddit. All the code is now available on GitHub. Every episode I'm going to upload the code, so I'll share a link to that below as well. And please consider subscribing if you want to see more of these videos. Thanks very much for watching, and I'll see you next time.